for Team SAE Aerial Design Team. My team members are Claudia Zaguir, Luis Valejos, and myself, Fred Abdala. Okay, so the objective of our design was to be able to build an aircraft that could carry the maximum amount of weight as possible consistently, while keeping the manufacturing cost, the manufacturing time as low as possible, and to be able to have both stability and control. Now the bigger picture, what was the importance of this project? This project was paid for by Lockheed Martin, and what they did was they got a set of requirements from their customers, and out of those requirements, they made a set of rules for us to follow. So that's why we had different requirements, like the payload that we had to carry, the payload area, the electric motor and such, and then they used these specifications and all the innovations and ideas that all the teams in the competition gave them, they used that to sell them off to their clients, to be able to fulfill roles in the military, in disaster relief, domestic policy, sports, armed attack, and such. So the competition. For this year's competition, there were 75 teams that assisted. There are 3 classes. There's regular, advanced, and micro class. The difference between the advanced class and the regular class is that they had to drop their payload into a specific part of the path of the field that we were in that day. So the competition was held from Georgia from April 11 to the 13th, and the score was based on a written report, an oral presentation, and the ability of the aircraft to carry the load successfully through, in this case, 5 rounds. So what are the requirements? We had to have a combined length, height, and width of 175 inches. We had to use an electric motor that required a single LiPo cell battery of 4 cells of 14.8 volts, a 1,000 watt power limiter, which means that we had to get the motor that could be as close as possible to 1,000 watts, but not above that because the power limiter would cut it off. We had 400 feet for takeoff and 200 feet for landing, and we had to have a maximum weight of 65 pounds, including the payload that we were going to carry, which no one even came close to in the competition. Now for the global learning. When it comes to the engagement, as I said before, thanks to Lockheed Martin, this was not an individual project because all of our ideas from all the teams, they put them together and we were all working towards a single goal, to be able to design an unmanned aircraft system in this case for Lockheed Martin. And then for the lower awareness, excluding the LiPo cells battery, which are really inflammable, we used materials that would not harm the environment or anyone in the competition in case of a crash. And then finally, for the inside, we worked with someone from Venezuela who already went to the competition, who gave us his tips and his knowledge so that we wouldn't make the same mistakes. These are the process and the timeline that we used to be able to fulfill not only the competition's deadlines, but also the university deadlines. And that path that you see up here is the same path that we took for our presentation. So first off with the research. For the research, we took into consideration all the 3 wings positions. So we started out with the low wing and we said, well, we can't use the low wing because it has low clearance and because the air velocities, when the air velocity change, that can be the difference between a successful landing and a crash. We try to use the mid wing. You can't really see it here because of the projector. But the reason we didn't use it is because although it has good stability, we had to consider the external loading by attaching the wings to the fuselage on that side. And we also, so the other reason we didn't use it was because, because it was really hard to transport. So using a high wing, which we did, is a detachable wing, a detachable tail, and a different battery compartment, that would be easy to transport and be able to take it to Georgia safely so that the plane got there in one piece. And also with the high wing, the benefit is that the center of gravity of the plane is actually in the middle or in the center of the payload area. And that way we can fly the plane, the center of gravity will be in the same place with and without the payload. For the airport, we did the CFD analysis and we used the Profili software. And as they will talk after me, we came up with the decision that we were going to use a deep camber airfoil. And we used an S1223. And that airfoil was not only the one that we used, but we found out that most of the teams in the competition, they use the same type of airfoil. Now for the wing shape, we were going to go for we tried to go for a taper or elliptical wing, but because we didn't have it was too expensive and the skills required to build it were too high, so we decided to go for the rectangular wing as you see there. Now, for the fuselage, we had to consider, because of the payload, we were changing payload, and not all the rounds we use the same load. So we had to consider all the forces that come up with this, not only when the plane is on the ground, so the tension, compression, bending, and torsion forces. We had to consider them not only when the plane was on the ground, but also when it went airborne and when it was doing turns and such. For the tail types, we used a modified version of an H-tail. As you can see in our conceptual design there in our poster, that was how it was originally. We changed it like that. The reason is, with that design, we only had to use one servo, and using the H-tail, it actually gives us the same stability as using a vertical stabilizer. And with that, we could get a lower clearance, so we had a bigger wingspan, and that's why our wings are so big. Now, this is the trade study that we did. You can't actually see, but it says option A, B, and C. We came up with the decision of using option C with a rectangular wing and the modified version of the H-tail, which was the most efficient for us. Finally, that was our conceptual design 4 months ago, and we studied the winglets, the ducted front propeller, the retractable flaps. The reason we didn't use them is, first of all, the winglets, according to our design, it would only increase the efficiency of the lifting force of the plane by 3%. It was too much work for just 3%. Then we had the ducted front propeller, which was on top of, we were thinking about placing it on top of the wings. But then that would have problems with the CG, and also it was too heavy. And the plane as it is right now, it's too heavy, it's 14 pounds. And then the retractable flaps, which were also too heavy and they were too hard to manufacture.
Okay, for our preliminary design, we used Sadler's-Mohammad's method, which uses performance requirements to obtain an initial surface area and power required. To start off this method, we used to calculate the total weight of the aircraft. This is done by adding the payload weight, the empty weight, the crew weight, and the fuel weight. Since our airplane is an electric motor, then the crew, and there's no crew, we just have the payload weight and the empty weight. Since the competition does not limit us on the rate of climb, neither does it limit us on the ceiling, our calculations were based on the takeoff run, the maximum speed, and the stall speed. So these equations were manipulated to have them dependent on the weight to surface area ratio and weight to power ratio. Using our parameters, we obtained the following plot. Anything on the left of the vertical plot indicates that we satisfy the requirements for the stall speed, and anything under the curve satisfies the requirements for the maximum speed and for the takeoff run. In our design part, we were able to obtain a surface area of 1.28 meters squared and a required power of 921 watts. Once we already had an initial surface area, we decided to go for the airflow analysis. We used Profili to compare different airflows that had been suggested for low Reynolds numbers. In here, this is the coefficient of lift against angle of attack and coefficient of drag against angle of attack. We chose the CILIC 1223 because of its high lift characteristics. Then this airflow was put into CFD analysis so we can analyze the pressure distribution. What we obtained is that at a 0-degree angle of attack, there's very low pressure distribution. Therefore, we decided that our wing had to have an incidence angle of 3 degrees so that we can have the desired lift at takeoff. The wing design, we evaluated the aspect ratio. The aspect ratio is inversely proportional to the induced drag of the plane. Therefore, a higher aspect ratio will have high moment of inertia that needs to be overcome, and a lower aspect ratio almost behaves like a plate. So we decided to go for the recommended that is between the range of 5 and 7 for an aspect ratio. We also added a hydro to our plane so it can help stability when it's flying. We use reinforced by using webbings in a structure to keep it light. And we also have this struts so that the wing doesn't have to be as heavy, but it can take the load at the maximum load. As Fred mentioned, we decided to go for a rectangular shape to ease the construction and also because it will reduce our manufacturing costs. We performed some analysis on SolidWorks to see how the wing loading on the wing. It had a factor of safety of 2.6. This was then validated by using experimental testing where we loaded our wing with 60 pounds and it did not break. We did not perform a destructive test because we did not have any wings to spare. For the lifting line theory, we evaluated using a MATLAB code. A elliptical profile means that the shape of the wing, the distribution is good, and no further changes need to be made to our design. For our landing gear, we decided to go for a tricycle configuration. The rear back landing gear was custom made. We use SolidWorks to simulate 37 pounds of load, and we obtain a maximum deflation of 1.51 millimeters. This was then tested by adding 37 pounds into our fuselage, and we tested a deflection of 1.26 millimeters, which correlates with our results. For our control surfaces, we use the rule of thumb, which is for ailerons, you have 25% of the chord and 25% of the wingspan. For the rotors, 25% of the stabilizer area, and for the elevator, 12% of the stabilizer area. When we had already our control surfaces, then we went ahead and used the formula used that you can read so well to calculate the torque on each of the control surfaces. By using this, we can calculate what is the surface that we're going to need to buy for our airplane that are going to be installed. The following plots represent the surface deflection of each of the control surfaces and the amount of torque that will be seen at each position. One of the techniques that we used was to make sure that we keep our airframe light. This was a weight reduction technique. The first technique was we analyzed the fuselage in between a one-piece construction and several pieces glued together. The one-piece construction had a lighter frame, and it also had a factor of safety of 2.6, which was twice as much as the pieces glued together. We also analyzed the wing configuration. We analyzed having plywoods at a greater separation and having plywood at the key locations of floats and balsa in the other locations. The plywood had a better outcome. They both had a high factor of safety, but when it came to construction, we realized that it would not have been easy for when you're shrink wrapping the wing to use the plywood with that much separation, so we ended up going with plywood and balsa for our design. A very important factor in every design is to make sure for the aircraft to fly is that it's stable. To accomplish this, we made sure that our center of gravity was located at the aerodynamic center of the wing, which is at 25% of the chord span. This was because we wanted the center of our payload to be located at the center of gravity, so that when we're loading and increasing the payload, the CG will not change and it will be stable. To make sure that the aircraft is balanced, we did some of the moments and make sure that they equal to 0. And now, Luis will continue with it.
In order to choose a motor for our airplane and propeller size, we had to start by the limitations that the competition put on us. It was 1,000 watts the limitation. We did have a battery, which was a 14 to 16 volt battery, it's a 4-cell battery. So from there, we choose a motor that would draw no more than 65 amps. From the two selected motors, we used some software analysis where we tested our propeller, diameter, pitch, RPMs with the motor, the given RPMs, and it gave us, in this case, this is one we show 18 by 8, we got 960 watts, which is under 1,000 watts, and 10.7 pounds of thrust. At the same time, we correlated these results with a modified version of the equations provided by MIT on propeller efficiency, where it gave us that by the same propeller, 18-inch propeller, same RPMs, we got almost the same numbers, 10.69 pounds. Okay, we also did some bench testing on different motors and propellers. We started by the recommended by the manufacturer on both motors. As you can see on the Rimfire, we started by is a 13 by 6.5 propeller. That was a recommended one. It only gave us 6.8 pounds of thrust and 537 watts. We needed to maximize those watts in order to get the most thrust out of our combination. After testing the Rimfire up to 18 by 10, that's what it says on the bottom, we went over to 1,400 watts. So instead of reducing the pitch, instead of reducing the diameter, we went for a smaller pitch. And as you can see on the E-Flight, which is the one that we use, we got 10.8 pounds of thrust, which correlates almost exactly with what we did analytically, and 960 watts. That is the propeller we use for competition. The tail design, since we have a short fuselage, we had to make sure that the surface area of the horizontal stabilizer, as well as the vertical tail, rotor and elevators, we had the proper size in order to steer the plane. We used some of the home built parameters, which are mentioned for vertical and horizontal tail volume, in order to come into the Reimer's, it's Reimer's plot, basically, it's out of a book. Well, we're trying to avoid the wake of the generated by the wing. With our tail arm, core length, same thing as the height and the core length, we needed to land to the supersonic section of the plot, and that's what we're trying to achieve. On the manufacturing, as she mentioned, we started with balsa wood, we implemented some plywood. At the same time, we had to use spruce to give more rigidity to the wing. We use epoxy and CA for gluing, basically for binding this stuff. As you can see here, we started by the single ribs that are designed for the ribs, and the construction just followed by attaching the spruce, the box on the outside, some of the tail, and this is the beginning of the fuselage. That's about 50% of the construction. Okay. After the wood part, let's say, was done, we had to do the assembly process. In order to give it the finish that it has, the looks that it has, and to cover some of the structure, we use a shrink wrap called Ultra Coat. That is what you see on the outside. At the same time, we had to make all the electrical connections and several mountings. And then the most important, check the balance for the airplane. This is a breakdown of our cost analysis. As you can see, roughly 50% of it is based on travel expenses and registration. The other 50% is on materials and parts, electrical parts that we have to buy for the plane, which are not cheap, they're actually expensive. The total amount to, we're missing the $3,500. We did some flight testing. We were not able to do as many as we wanted before the competition due to the time constraints with our pilot. We were able to perform 3 successful flights, one with a suggested propeller, the 15x7, which it really didn't have enough thrust to take the airplane. It did airborne, but it was very slow, it didn't have enough power. The pilot did not feel comfortable with it. Then we tried the 18x8, which is the one we had bench tested, and with only 1 pound of load, and it was a completely different airplane. And the third flight was only with 7 pounds, and based on what the pilot said, he said it was a great plane, easier to fly with the weight than without the weight. And that is what we did before the competition. Here's at the competition, we had the first day, we had a technical and normal presentation, and on Friday and on Saturday we had 5 rounds, 5 test flights. The most successful one was with 16.6 pounds, and the second one that we were able to get was 7.5 pounds. We ran into some power limiter problems that we had to fix at the competition, and we were only able to fly at a 70% of the maximum power we had calculated. Here are the results of the competition. For the maximum payload, we placed 8th on a competition, international competition of 42 teams. Within the teams from the USA, we placed 4th. As you can see, we have 2 teams from Brazil, 1 from Poland, and 1 from Canada above us. Okay. As a conclusion, we learned the managing skills to start a project from the beginning to the end. We really had to manage our time wisely. We obtained I would say some school recognition at the event, since many people did not actually know at this event where Florida International University was located, not even that it was South Miami. So from there we got some recognition as well. And we have some future recommendations for the following teams. We know there's another team doing their airplane as we speak. And for 3 people is a lot of work. It'll be very, very good if they can get at least 6 people, 3 seniors like we are, and maybe another 3 juniors or sophomores that will get involved in the competition years ahead of time, in order to have a better view of what the whole competition is about. Since we did not have it, and we could have done much better. That's what we think. We would like to start an FIUSA team in order to do a fundraiser for, as I said, it comes out to be expensive when you want to go to the competition. If it was just building, it would have been a different story. We would have showed up here with just a plane. And that's about it. There's a test flight. I'm not going to have time to show it.
Yeah, we got
Okay.
1 minute, last 2 minutes.
That is actually one of our test flights with 7 pounds. And if anybody is into modeling airplanes, they know that they always try to get the highest plane, the lowest weight, in the air.
This was also, the plane was flown with around 20 miles per hour of crosswinds.
Wow, excellent. That's why you took off today.
Yes.
Yeah. You can see it in the pilot.
Took off really quick, about 10 feet.
Well, the camera is not that well, but it's more still when you see it fly. It doesn't move that much. It's a stable plane. Another 30 seconds. Planes under control. That's what the pilot said.
No airbags?
No,
No,
no.
they were not required.
You actually get
Would be-
disqualified in the
yes, for
competition if you
airbags.
have any airbags. Then it should be landing.
It's coming, don't worry. It'll come down there. It was done in Cape Coral, the test flight. Since our pilot, as I said, some time constraints, he lives in St. Petersburg.
Yeah, it's more-
So it wasn't as easy to get a hold of the pilot on flight.
There you go.
That's our special secret.
Okay, all right. Any questions for group one? I'll start off. You want to go?
Go ahead, sir.
What was the LOD ratio on this final airplane? Lift to drag?
I think it was point, I can figure out.
It's in the report. It's on the
Okay,
report.
all right. That's why. Why no flaps? I noticed it landed well without flaps.
It was,
Why no flaps?
since the airport we choose is a deep camber, it really creates enough drag and lift to work kind of as if you would have flaps down at all times. That was one of the main concerns. Another one was the construction. It was out of our area of knowledge of the construction part, because we wanted to be retractable, to come out and down, and it would have been more weight for the plane too.
If you saw from the Profili graph that we had before, this airport is the one that has the greatest lift, but it's also the one that has the greatest drag. So that's why it's a perfect combination. But
So
it's
I
what we wanted to do.
A recommendation maybe for the other teams would be to use a Clark White, which is more of a flat bottom airfoil, but it also has a high lift, and you can add flaps, that way you can reduce the drag while you're taking off.
It's Clarkwell would be a much easier to construct wing. We have, once we cut the laser cut the ribs, they're like paper thin in the back. So we run into the problem there where we had to find a way to construct it without breaking the ribs itself when they were not as a whole.
Okay, I noticed you've got twin rudders. Is there additional drag because of that? And how did you manage that?
There is additional drag, I mean, compared to using one rotor. But since we needed the surface area for steering, like I said, for a short fuselage, we didn't want to go higher on our rudder, since we had those high limitations in total wingspan limitation, and they're only checking the highest point of the airplane. So that's why we decided to go with two rudders. It was a give and take situation.
So what is a target payload for this?
The predicted load was 22 pounds. However, we were only, as we said before, we had some problems with the power limiter. We were only running 70% of the efficiency, but we managed to lift 16.6 pounds of weight on the payload, and that gave us 8th place. So if we would have run at 100% or 960 watts, like we said,
Our testing
we would have easily got to the predicted load that we had.
All right, those are my questions. Dr. Basil?
Sure. So you had a very interesting comment that I picked up. I spoke with you guys a little bit about this, but I think the most important part of this specific type of flight is stability, right? And you guys did a really great job of identifying that and using some good theory. But one thing that you said, Louis, that stuck out a little bit to me was the pilot said that it flew better with the payload than without it.
Right.
If the payload is at the CG, can you explain why he felt like it flew better?
Because of the wing gust. The wing gust, since the high lift produced by the wing, it was harder for him to land it at the speed. I mean, instead of shutting the motor down on the coming into the
Final
land,
approach.
And also, we said that day that he said that, the pilot said that, there were 22 miles cross winds.
Sure, so it's more about momentum of the plane.
Yeah.
Right.
And that's why the flap was necessary. So,
Well, sure, yeah.
Okay.
But I mean, I don't know if you can necessarily expect 20, I mean, you can't.
That was
Yeah.
one of our main points of the design. The design started from there. We located the CG of the plane, and placing the CG right in the middle of the, that way we can apply it with or without.
Yeah, right, I mean, it's a very critical thing, right?
Right.
Or you can change the thing. Can you talk a little bit about what recommendations you guys made actually to Lockheed Martin at the end of it? So the whole point of the project was for you all to make some recommendations to them about it.
Well, it's not really to make a
Okay.
recommendation. Lockheed Martin uses this event to see the ideas that the teams can come up for the design. Our goal was just to make an aircraft that can be stable and that can hold the load that we wanted to predict. We have to make our presentation to 4 engineers from Lockheed Martin, and from that presentation, from our conclusions and from the conclusions from our teams, then they evaluate if there's any data that.
So what would be your conclusions, I guess?
Well, what we got as a feedback is that it was the struts. They were very impressed that we used struts because it's not very common in this type of planes. And they agreed that right now there's a technology that's coming up to make the wings less
We're talking
heavy.
about commercial
Yeah, by using
planes,
these
probably
struts.
going into struts.
Yes.
Yes.
So that was our innovative point in the design that was picked up by the engineers.
That's it, Dr. Basil?
Yeah, I'll do some.
The question I'd like to ask is, it's pretty apparent from your trial that you had a very experienced pilot, and that he made a very quick move at the very end of that run in order to save a bailout at the end. How would you change things to make that plane capable to hand it to a less experienced pilot? I'll use that example because I'll use example. The next team that's coming through may not be able to get their hands on a fellow that's that capable.
Like I mentioned, I would change the wing profile, have a Clark Y. It's an easier to fly airplane when you have the different profile because this wing generates too much lift. Sometimes it's harder to control. So add a Clark Y profile into the wing and add flaps to have the lift like this time.
Also at the landing, you saw that he was dealing with the wind gust and seeing which direction it was coming. And we were lucky on our side to have this type of pilot for the competition.
Pretty clear.
So the more amount of control surfaces that you put on the plane, the heavier the plane will be. So making the plane more stable could actually lead to the downfall that you can carry less weight.
Less weight, so that's the design. Okay, and I'm assuming, like most projects, that there were things that didn't work. Talk to me about some of them and how you worked your way through them.
Well, initially, the first, one of our main, I guess, defects in our design was that we had made the H-tail, initially we manufactured it like this. Once it was already constructed, it was very difficult to have both rotors connected to one servo because we didn't want want to have two servos in the back of the tail because that would have too
It
much
wasn't as
weight.
stable actually as it is with.
Yeah.
We were not able to, even though with linkages, they would have a deflection
Yeah.
when it would be straight.
It wouldn't get it perfect.
It wouldn't get
Right.
it perfect. So instead of bringing it closer, and the linkage is much shorter to have that type of movement. And we kept our two servos towards the CG of the plane in order to keep it balanced.
Any other question? Oh, Dr.
What would you do differently next time so that you could operate at full power?
Well, actually, this time the problem was, as I said, one of the biggest problems was the power limiter, and that was because it wasn't calibrated. But we were not the only team that had that problem. We had all around our tent, all the teams were testing the engines, and it would shut it off at 700 watts. So the plane would be in the air, shut off, crash.
Yeah, the issue with our power limiter, the thing is that these power limiters are made so that when you pick the 1000 watts, it will keep the speed stable. Our speed controller, the one that we chose, which was a very good quality speed controller. And what it did is that it sent a feedback of the peaks instead of the average. So it will be, instead of keeping our limiter stable at 1000 watts, it will shut off completely the engine
Before
at
that.
700 watts.
Because it would feel the peak before it's coming, so it would send a ghost feedback to the power limiter. The power limiter would feel it, turn off, and then the engine would go.
This was also the first year of this competition done with a fully electric motor. And we were in the learning process as well as the people that organized it from Lockheed Martin. They said, well, we didn't expect to have these problems. throughout this competition, and they really try to help. And it's just, the recommendation from them was just go out and buy a cheaper speed controller that won't be sending this feedback to our power limiter.
The way we were able to be able to fly the plane, what the pilot did was that he would pull the full throttle of the plane, he would trim it, and he would put the full throttle of the plane at 700 watts. But that would take,
70% of the.
it took 2 minutes in the second round for him to be able to calibrate that so that he could go full throttle. Because in round 4, he didn't do it correctly, and when he went full throttle, the plane shut off the engine. It went out like at a lower speed, and the plane had to, land. So we couldn't do the fourth round because of that.
Any other questions?
Yes,
Go, sir.
congratulations, nice project.
Thank you.
This question is for Louis. What do you find the most challenging aspect of working in a team?
The most challenging part, it will be collaboration. We work hard together. Sometimes we need to pick up in others' work. That's about it. I mean, sometimes I have some expertise in one part, she has some other expertise. Fred's got his own set of expertise. So sometimes I will be trying to do it myself, maybe some more of the manufacturing, and there's so much to do that she will have to come up and help. It's just the balance of the team. But that's about all the problems we have.
And the success of the team is the success of the project. Not to diminish what you were doing, I am a kind of a tick-attack type lady. Are you able to pull up your first slide that Louis had that's titled Performance at the top?
The first one that we've had,
Yes, right there.
this one.
As an outsider looking at this particular display, I find it very confusing. There's lots of colors, there's lots of fonts, there's lots of things going on here, and me trying to pick up what you want me to get from this, I find it difficult.
This was basically a print screen to show
Yeah,
that we are
from
using
the software.
a software, not just throwing numbers there from a table that we created. This is the reason why we have all these colors. Right, the software was called Static Cross Calculator, okay, and where our inputs were only the propeller, the pitch diameter, the RPMs of the motor, and the air temperature. Okay, from there, we got some results. Of course, we don't know if this is how much we can trust this software. And we went to
It's an estimate, we proved it twice.
My point of my statement is not so much for
Yeah,
you
it's not
to
Yeah.
explain what you have up there, is that as your audience, usually your audience is not going to be as knowledgeable as you are in what you are doing. You're very lucky to have engineers here who actually understand what you're saying. But usually your audience is going to be more generic, and so you want to make sure that the visuals that you present to them give them the information that they want and not too much more. Okay? Do you have access to your report? You have a number of parallel construction issues in your report. For example, just to let you know, when you do a bulletin point, you want your grammar to be consistent. You don't want sentences with phrases. You want to make sure that when someone reads down the line, you have common grammar going across your issues. So you have a lot of that throughout your entire report. So I ask you to take a look at that.
That's
Thank
it?
you.
All right, thank you. That's it.